let's do this. I'm going to erase all this stuff and go for it. So the first thing we need to always do in a titration is figure out the moles of stuff we got going on. Okay? So calculate your moles. Right here, all three problems are going to use this amount of moles of HF. So it's 0.05 liters times 0.1, which is 0.005, right? All right, that's moles of HF. In a titration problem, we are neutralizing that acid by adding base. Okay? So the next thing to do for each one of these, and let's just do them all while we're here, is to find the moles of base that I would be adding. Is that fair? So I have 40 milliliters, which is 0.04 times 0.1. So that's 0.004 moles of OH minus. Okay with that? And this isn't too hard. Then this would just sort of be the same. So it'd be 0.005 moles OH minus for B and 0.006 moles OH minus for C. Good so far? All right. So you have those numbers down because I'm going to erase them. But here we go. So the first one, I have 0.005 moles of HF. I have 0.004 moles OH minus. In this, chemistry before math, what happens is the H plus reacts with the OH minus to form water. You okay with that? And if it's water, neither the H or the OH minus contributes to pH anymore. They're tied to each other, so they don't contribute to the pH. So what's left over then is 0.001 mole of HF, right? You okay with that? But in the chemistry, this was now liberated, so how much F minus is there? 0.003 moles of F minus. This is a buffer. Okay, we did the math before. It's the same idea. Thank you. It's 4. That's why you all made a weird face, huh? My fault. Yeah, I don't know where I got the 3 from. I hate this new button. There we go. Thank you. All right. So now, if I have a weak acid and a conjugate base, I know that I have a buffer. And I was comfortable last week using the Ka and Henderson-Hasselbalch to find the pH. So the pH, I will remind you, is equal to the negative log, all right, of the Ka, or pKa, that's just that written out, plus the log B over A, right? So I take the negative log of 1.8 times 10 to the negative 4th plus the log. The base is the F minus, 0.004. The acid is 0.001. And then I just plug that into my calculator and I go from there. Can I get some calculator help there? 4.35. All right, that's our zip code. All right, 4.35. Make a note to yourself, because this is some of the hardest things we're going to do. Below the titration curve, calculate the amount of weak acid left. Calculate the amount of conjugate base left over, or produced, or whatever, liberated, and then use Henderson-Hasselbalch. All right? Are we okay with that part? Now, once again, that math only applies to the first part. That math only applies there. with me? Okay. I'll pause this for a minute in case you want to write stuff, because I'm... All right. So Jeffrey just asked, how does someone know it's in this part of the graph? All right. So to answer that, if you have any excess weak acid, you're still in this region. Okay? So you have to do the math. You don't know where you are until you do the math. But if you have excess acid, you have not neutralized it all. So you're not at the excess, or at the equivalent point, I mean. And you definitely can't be above if there's still some, because it would be completely gone as well. Does that make sense? Okay. All right. So the next math question refers you to the middle. And the way you would know it was the middle also is because the math, you're going to end up with it being equivalent. All right. So I'm going to erase all this. And we'll do this one. We still have 0.005 moles of HF, right? But in B now, we have the same 0.005 moles of NaOH. And it is extremely tempting to say, oh, okay, this is neutral because my acid and my base are equal. And that's true in strong acid and strong base land, but we're in weak acid and strong base. All right? So that is not true, and the math becomes trickier. When you do this, you find that you have 0 moles of HF, right? But you have 0.005 moles of F minus. Are we okay with that? All of the F minus has been liberated or detached from the H plus. All right. Now, F minus acts as a base. Remember, a base is something that will accept H plus. Since F minus is the conjugate base of a weak acid, it will grab an H and tie it to itself, which changes the concentration of H plus, which makes the pH get higher. All right. So this is a little bit tricky, but we're going to be fine. So what we do is we now take the Ka and we have to solve for Kb. All right? Because we really need, I'm going to put an arrow, we really need the Kb since this acts as a base. Okay, this is the slide that I talked about before. So if we know Ka is this, Ka times Kb equals Kw. So we just divide them. And Kw is 1 times 10 to the negative 14. We're going to divide that by this value, 1.8 times 10 to the negative 4. And someone tell me what that answer is. Louder? Okay. Are we okay with that value? Someone else have that on their screen? All right. It's pretty reasonable, so I'm sure it's right. Okay. So now what we're going to say is that my Kb is equal to x squared over initial. But remember, red flag, if it's Kb, then x squared, my x is equal to my OH minus concentration. Okay? So if we're solving for that, remember when we do this, we're going to find the POH. So we just have to take that extra step to subtract it from 14. All right, so I now have this 5.5 times 10 to the negative 11 is equal to x squared over the initial amount of F minus that I had. All right, now I come up here, and this one is even more tricky. We got to be careful, because this is concentration. So I have this many moles, but I must divide that moles by the total volume, which was 50 plus 50, which is 0.1 liter. Okay, so 0.05, right? All right. Now, this would technically technically be minus x. But remember, we ignored x because we're talking 11 zeros, essentially. It's going to be so small the math won't matter. So we're going to get rid of this, and we're going to solve now for x. Will you solve for x? So what did x end up being? Negative what? 6. All right. That's a lot of 6s. Now, I need to take the negative log of that value, right? And that will tell me the POH. What's that? 5.8 is my POH. But does the problem want POH? No. It wants the pH. So I take 14, subtract that, and I get 8.2. Ooh, got lucky there. Because I made up this stuff. Early on, I was like, wait, what if we do this and we end up acidic? Then I'm screwed. All right. Does this seem reasonable? Sure. That's the answer right now with what you know. All right. This is, according to the math, we just found the equivalence point of when a weak acid is titrated with a strong base. And according to this, it needs to be greater than 7. Now, it's not going to be off the charts greater than 7. It should be close-ish to 7. And we were, especially for made-up numbers, we were pretty close. Okay. Tricky? Very, right? I know it is. I warned you that this chapter has some tricky math. But it's doable as long as you do the chemistry right. Then the math is usually not awful. Okay, do you need any time to take any notes on what you did there? So, just to summarize it, you have a question or you just need time? Initial. I is initial, which was your concentration, and that's why we had to do this step, because it's not just moles. In Henderson-Hasselbalch, we can get away with moles. That's fine, because we divide both by the same number, and there's no squaring. So it can be ignored. Here we use concentration of F minus. And when we say initial, it's the amount we made and then the chemistry that would happen there. All right. So one more time in a nutshell, and this one's kind of hard to do the nutshell. You do the math and you see there is no more of the weak acid, which means there is just conjugate base. If there is just conjugate base, then we have to find its concentration. That was this part. And then we find its Kb, which was this part. And then we're ready to plug it in to the Kb equals x squared over the initial concentration. That was there. Kb was here. We do the math. We solve for x. X is technically the OH minus concentration. So we take the negative log of that, which gave me POH, which I subtract from 14. It's a lot to put in a nutshell. Like that's a gigantic walnut shell right there. We're not talking whatever, pine nut. Okay, part C is not that bad. The reason why part C isn't bad is because now, so we had it kind of whatever and then flat, because now we're here, and if we're here, that means we just have concentration or excess OH minus. All right, if we have excess OH minus, it really doesn't matter what else we have because it will dominate the pH math by a mile. So we still have 0.005 moles of HF, right? But now I have 0.006 moles of OH minus. When I do this math, I have no more of this, correct? All right, I have 0.001 moles of OH minus. You okay with that? Now, is there F minus? Yes, there is. But if you remember, it's KB was something times 10 to the negative 11 versus this one, it's such a large KB, we don't even calculate it, like it's 10 to the almost the 0. So, yes, there's some F minus, but it is negligible compared to what the OH minus is. So, all we have to do now is take the negative log of 0.001, which is 3, and we take 14 and subtract that, and we get 11. Oh, I just lied to you. I'm sorry. Hold on. There was one more step here. This has to be concentration. I'm sorry. I feel really bad. So it was 50 plus 60, so it's 0.11. You okay with that? Sorry about that. Did I lose anyone there? Okay, let me, that was my fault. This was moles, but when we find pH or POH, we take the negative log of the concentration. Moles are not concentration. So you had to take your moles and divide them by the total volume, which was 60 milliliters plus the original 50. So that's 110, oh boy, milliliters, which is really 0.11 liters. Better? So we take whatever this number is, the negative log of whatever this is, and it's going to be closer to 2 something. What is it? Okay. 2 point what? 2.04. Okay, sorry about that little brain mistake. I know it's tricky. But all of them are doable. It's just tricky to know what I'm doing. What? Yeah, I do need to. Oh man, I'm just falling apart right now. Thank you. I do have to subtract that from 14. So 11.96? Oh geez. Thank you, kids. Thank you. That's what happens when I hold my slate crooked. Like you think you know where you're at, and you think your circle is going to be perfect, and it ends up to be an ellipse from the bottom to the top. Okay. This is probably some of the hardest things all year. So if it seemed hard, it's because it is. Yeah, probably. We're about it. All right. Now, this is not math. This is just some general stuff now. With weak acids, the initial pH is higher, and the pH changes near the equivalence point are more subtle. So the weaker it is, the less it looks like this, and the more it looks like that. Okay? This is strong. This is weak. Now, you don't really need to know much about this. You have to be able to see a titration curve, like the graph, and know what it is. You don't have to do math on it, but like if you saw this, you'd say strong and strong. If you saw this, weak and strong. If you saw this, weak and strong. If you saw this, strong and strong. Okay? The difference between these, this is a strong acid being titrated with a strong base. Weak acid, strong base. Weak base, this should be flat. Strong acid, strong base, and strong acid. Because everything we do goes both ways. All right. The pH, we already said it's, oh, sorry. This is a weak base and strong acid. This time it'll be less than 7. And you know what? Mentally, these are not that bad because whatever the stronger thing is, you're going to end on that side of the pH, or that side of neutral. So if it's strong acid, you're going to end more acidic. If it was a strong base, you're going to end more basic. Okay, you do need to know what this curve would mean. You'll never have to do math on this, but you have to recognize that if a titration has 2 bumps, it's just a polyprotic acid, meaning that the H's break off as you move along, and they each have different equivalence points. Now, the math on those is super hard, and I've never even had to do it, and I have a minor in chemistry. So we don't do the math there. We just have to recognize the shape of the curve for a polyprotic acid. What does polyprotic mean again? More than one H. Okay, so here's just kind of a summary. I got to sneeze again. So you have to be able to recognize what they are, and you also need to recognize and know where the equivalence point would be on the pH range. All right, strong and strong either direction. It's flat on the top, flat on the bottom, and your equivalence point is at 7. All right? Weak acid, strong base. It's sort of ramped in the acidic, and it's flat on the base, and the equivalence point is greater than 7. Okay, so that was the top right one. The bottom left, weak base, strong acid. It's got like a ramp instead of being flat. It slowly changes here, then it goes straight down, and after the equivalence point is less than 7, all right, and then it's flat again. In polyprotic acid, we don't need to know where the equivalence point is, because like this one would have 3 of them. That would be really tricky math, but you just need to recognize the shape. Are we okay with that? I'll leave this up for a minute.